This video will show you how to do the possible bonus at the end of the work homework. I will do number 32 because it's the more complicated one. If you can do 32, if you can follow this, then you can do 31 because the only difference is it's easier because the initial velocity is 0 instead of non-zero. All right, so this is the goal. Work is done on an object, and the object's initially moving with an initial velocity of vi, and we know its mass. And the goal is to prove that the amount of work done on it, the total work done on the object, will equal this strange expression here, 1/2 m times final velocity squared minus 1/2 m times initial velocity squared. And since these are squared, and they can be just called speeds from now on, because if you square a negative, you get a positive. All right, so we're trying to prove that. And like all of our proofs, they're done by substitution and using things that we've already learned. So we'll start with something we've already learned, which is the definition of work. Work is defined as the force you apply to something times the distance it moves. The left side is already done. We want work on the left side, and we've got work on the left side. But look at the right side. This is force times distance, and that's not here at all. What we want in our final answer is this crazy mess here, which means we have to make substitutions into this until it looks exactly like that. This is the most complicated proof we've done so far this year. So let's start substituting one thing at a time. We'll look at force. What do I have? I have only one rule for force that doesn't specify a particular force, and that's F equals ma. So what we'll write over here is but F equals ma. So that means anywhere we see F, we can replace it with ma. So let's do that. Work equals MAD. That's progress, because now we have an M, and we need an M in the final answer, and we've got an M. But we also have an A and a D. This is now suggesting those equations of motion from the first semester, because we've got acceleration, and I remember there was distance in those, but we didn't use the letter D. So instead of D, what letter did we use in the equations of motion? We used delta x. So we're just going to switch letters. Now we could have defined work as F times delta x to begin with, but I don't like to do that because it really is distance. It's not a particular change in position, and this is much easier for students to understand. But in this proof, which is a bonus, remember, you do have to be willing to make that change. Instead of D, you're going to use delta x. Okay, so work is ma delta x now. This is what used to be the F for force. This is what used to be the D, and we're making substitutions based on what we already know. Okay, so we want to keep that M because it's in our goal. But A and delta x are not in our goal. VF squared and VI squared are. So now think of these four letters. How are they connected? A, delta x, VF, and VI. They're connected in one of our four equations of motion from the first semester. And it's the fourth one. VF squared equals VI squared plus 2A delta x. We're going to do something you may have never seen before, and you definitely haven't seen in this class before. Instead of solving for a single letter, we're going to solve for a little group of letters, because see how I have A delta x here, and there's A delta x there. If I could isolate this here, I could take whatever I get and put it in for that and replace this so I get rid of it. So let's isolate this. You get A delta x. I'm not going to go through all the algebra, but you subtract this from both sides and then divide by 2. VF squared minus VI squared over 2. So that means A delta x is exactly the same thing as this. This is two ways of saying the same thing. If you calculated them in a particular specific problem, this would be a number, and this would be exactly the same number. So anywhere you see A delta x, you can replace it with VF squared minus VI squared over 2. So let's do that here. So work is M times, and this is how you do a replacement. Don't just try to shove it in and maybe make a mistake and only multiply the M times the first one. Put brackets, empty brackets, and then what used to be here, you replace the new thing in the empty brackets. That way you'll get issues like distributing correct. Okay, so this M is multiplied times this whole thing, and it's a little tricky because it's distributing and there's a fraction involved. But if you do it correctly, you get this first term, 1/2 times mv final squared minus, and then the M goes to the second one, 1/2 times mv initial squared. And that ringer, that was to remind me that class is starting soon. Okay. All right, so there's the thing we were trying to prove. And I'll tell you two more things now. An old-fashioned thing to write at the end of proofs, you'll still see it in books, is QED. That stands for Quod Erat Demonstrandum, and of course it's Latin. And you can almost see what it means from its similarity to English. This is the thing which was to be proven or to be demonstrated. That this answer here, this is the thing which was to be demonstrated. And that's traditional to put at the end of a proof. There is no other thing. There's no modern English equivalent. So if you want to signify a proof is over, this is the traditional way to do it. The second thing to tell you is we learned 9 types of energy in class, and this here, this term, 1/2 mv squared, 1/2 times the mass of something times its speed squared, that became called kinetic energy in the 1800s. So when we learn the term kinetic energy in class, this is the formula for it, the formula, the only formula for kinetic energy in classical physics. So whenever you hear kinetic energy, if you want to think at a college level, you think this formula, 1/2 mv squared.